Hey everybody, in this video I'm going to go through some questions on linear versus exponential models. Let me just make sure my screen shares. Good. Okay, so the value of a certain investment over time is given in the table below. Answer the questions below to determine what kind of function would best fit the data, linear or exponential. Now, I know this section kind of looks intense just because it has a table and all these drop downs and such, but I promise it's really not that bad. First, I want to just clarify the difference between a linear versus an exponential model. So a linear model is going to grow or decay, grow, increase, decrease by adding or subtracting a constant value. So if I add by 2 over and over and over, that's a linear model. If I'm subtracting by 0.5, if I'm subtracting, that would be a linear model. Now, exponential, they grow a lot faster and will always exceed a linear model. Linear grow by adding or subtracting. Exponential grow by multiplying or dividing a common ratio. Now, oftentimes this constant is referred to as the common difference, whereas what you are multiplying or dividing by, that is a common ratio. All right, so looking back at this table here, we have the number of years since the investment has been made, 1, 2, 3, or 4 years since it's been made, and the value in dollars of the investment. This is our f of x. Now, if I am looking at how my f of x values are changing as x increases, it looks like the value of the investment is going up, right? From 14, this is really like $15,000 to the next year, let's call it about 16, well, we'll round it to $16,500. And then the next year to about 18. And then the next year to even about, we'll call that 20. So it looks like we are adding or subtracting some number each year. And really, I would say adding because these f of x values are increasing. So I'm going to say that a linear function would best fit the data because as x is increasing, the y values are changing additively. We are adding a common rate on. So I'm going to say the common difference or slope because we are adding, and this would be the common difference. And to find the common difference, I'm going to need to actually subtract, right? So how much do we add from year 1 to year 2? So I'm going to subtract 16,357 and 4 cents minus 14,944 and 54 cents. And if I do that in Desmos, 16,357.4 minus 14,944.54 means we went down, we subtracted 13,000. Yeah, there's a typo. Felt wrong. There we go. That feels a lot more right. We did not go down. We were adding. We went up by 14,000 or 1,400, sorry. $1,412.50. Sorry, that threw me off there. I had a small typo, which drastically changed things. So if I take the second value, year 2, and I subtract away year 1, that shows that we added on that much money. All right, now let's look at between years 2 and 3. So year 2, we're at 16,357 and 4 cents. The next year, we're at 17,974.72. So I'm going to subtract away 16,357.4 from that. And luckily I already have one of these numbers typed in. I'm just going to clear that off and put it at the end. So now we are subtracting 17,974.72. And that gives us a common difference here this time of $1,617.68. And I put the plus sign because it is a positive number. That tells us from year 2 to year 3, we added that much to make it grow. All right, last 2 years I need to look at. I need to subtract year 4, which was 19,891.18 minus year 3, 17,974.72. So going back to Desmos and subtracting 19,891.18 minus 17,974.72. And now between year 3 and 4, oops, switch colors, we added $1,916.46. All right. I almost wonder if there is a common ratio. I almost wonder what would happen if I divide. If I divide 16,357.4 by 14,944. Is that common ratio the same as year 3 divided by year 2, as year 4 divided by year 3? And I'm gonna actually check real quick, because if it is, then this would be an exponential model. And it could be exponential in that it's growing kind of slow. So let's see. Luckily, I have all of the numbers already written out on the right-hand side. So first I did year 2 divided by year 1. So we multiplied by 1.09 or increased by 9%. How about? Let's look at year 3, 17,974.72 divided by 16,357.4. Oh, uh-oh. I had a feeling when these seem to be changing by an increasing amount each year. So let's just check the last two. Year 4, 19,891.18 divided by 17974.72. I'll be darned. So it looks like we actually are multiplying by a common rate here. So I'm going to almost rewrite some of this. Instead of subtracting all of these, we really divided. And this got a common ratio of 1.0945, blah, blah, blah. This was 1.09889, blah, 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 blah. And this was 1.1066, blah, 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 blah. So I'm going to actually return now to Delta with this newfound knowledge. I'm going to clear out what we had before because this was incorrect. This is actually exponential. An exponential function will best fit the data because as x increases, the y values change multiplicatively, meaning the common ratio multiplier or base of this function is approximately the same. We got different numbers each time for adding and subtracting. They were not about the same. So that's what made us change course. And that's okay. That'll happen with these problems. All right, now, how do I find what it is approximately? Well, I would say about 1.09 to 1.10. And I would round the second, and I'm going to even kind of write this out. I would round the second rate up to about 1.10. So let's just call this approximately 1.10. And I'm sure that will be good enough. I'm sure 1.9 would work as well. So let's see what answers it would like for this. Because at the bottom, it will tell you the range of answers that you can enter. Because it will vary, we might interpret it slightly differently. So it says here in red, the answer you could have put, we need to say it was exponential because they're changing multiplicatively. And the common ratio or base or multiplier is approximately, and that says somewhere on the range of 1.8 to 1.12. So if I had entered in 1.8, 1.9, 1.10, 1.11, 1.12, it would have taken it. Now, I think you should have entered in 1.9 or 1.10 because I don't know where else you'd get those numbers from. But these take some work. These take some practice. I honestly do encourage you to put this table into Desmos, and to remind you real quick how you would do that. In Desmos, I'm gonna clear all this. In Desmos, you would simply click over on the side here. I need to move this menu. Over on the side, this add item, and add a table. And then you could enter in your X and Y to see if it looks like it's increasing in a straight line or if it seems to be growing more and more and more or decreasing. Please let me know what questions you have. Be careful with some of these rates. These common differences or ratios could be negatives or fractions if the numbers are getting smaller. But always email me too if you get stuck.